I will start my presentation. Let's see if this works. Okay, can you see my presentation?
I can.
I can too.
Okay, perfect. All right. So yeah, thanks for the introduction. And today I want to basically, yeah, give an introduction about data availability checks. This will be, I'd say, quite. It's the basics. It's not like the latest research, but I just noticed that it is a difficult topic, and I want to help everyone to build a better like understanding and intuition about these. And so it's rather, I guess, a light-hearted presentation about this. And I hope afterwards you will, yeah, know much more on how they work. And I'll talk about light clients and fault proofs in the beginning, because that's basically the best setting in which you can talk about data availability checks, introduce the data availability problem. You can solve it using erasure codes. This is essential in sharding. We start with light clients, but actually, like, we'll see that for scaling blockchains that these data availability checks play a much more important role than just for light clients. And then in the end, I'll come to the subject of how we prove the correctness of the erasure codes, which is actually where the actual problem lies that we're doing research on now, or at least we have done for a while now. Yeah, and please feel free to ask any questions if you have any. I think it's not a problem if you want to interrupt or so. I think like we can take questions at any time. Okay, so let's start by talking about clients. So light clients and blockchains are basically clients that verify the consensus. So for example, for proof of work, that means that they check that they are given the longest chain, but they don't verify the correctness of all transactions. So that means that instead they only ask full nodes about those transactions that they care about, and they don't even want to know about the other transactions in a way, because they can't download them. For example, if you have a mobile phone, then it's not a great idea to download the full Bitcoin or Ethereum blockchain on it, because it's just way too big. You want a solution that still gives you all those nice blockchain guarantees, but doesn't come with a resource consumption. And using fraud proofs, which I will come to in a few minutes, they can actually be protected from the problems that come with not verifying the correctness of transactions. Okay, so let's have a look at how this works. So basically, this is like kind of a picture of the view that of a full node on top and a light client. So for a full node, they have block headers in blue, and then they also have the block data that corresponds to each block header, right? So the block header is something like, it has a hash of all the data that's in that block. So that's the transactions in the block data. And then it has some proof of work hash, for example, if it's a proof of work chain. At the bottom, you have a light client, and the light client, they've only downloaded the block headers. They didn't bother to download the block data at all. And now they want to have a certain transaction. I say, they ask the full node, can you give me like transaction 3 in block 4, please? And the full nodes respond with this, but not only does it give the data itself, it will come with a full proof that this is actually the data in that block. So that's kind of the nice thing about light clients, that they don't actually have to like just trust that the full node doesn't lie to them. They can verify. However, what happens now? Let's assume that in this block 4 there was an invalid transaction as well as the transaction that the light client asked for. So they will do everything the same, and they won't notice that there was this invalid transaction. So they were like, yeah, looks great, thanks. But they didn't notice that this chain that they have downloaded actually was an incorrect chain. So a full node would never have accepted this chain because, so for example, full nodes on Bitcoin and Ethereum, they will never accept chains that come with invalid transactions in them or so. Like they just discard them and don't include them in their fork choice, even if they have the most proof of work done on them. Right. So how do we solve this? We have we create so-called fraud proofs. So we basically have this policeman in this case, which could be any other node, could be anyone who has seen that there's an invalid transaction, can create this fraud proof, which is like a short description of what happened here. So they will give this invalid transaction, but they will also give the witness the proof that this was included in this block header 4. And from now on, all clients who have received this fraud proof will know, if I ever get a chain that includes this header, I should just ignore it because it's invalid. And I have a complete proof about it. Nobody could have lied about that proof because, yeah, it's it shows that it was included in that block. So basically here they say, no thanks, that's clearly not the right transaction, and they will mark this block as invalid in their own view. Right, so quick summary of fraud proofs. So they're short proofs that something went wrong. So for example, that a transaction is incorrect, or it depends on the chain. Bitcoin doesn't do this, but for example, Ethereum will always store the full state after transactions were executed. So it would include, like a fraud would include that you updated those balances incorrectly, for example. So the form of this fraud proof is basically, it has some pre-state. So this was the state before. Then it has the transaction and then the post-state, where this pre-state and post-state only need to be what the transaction touched, right? They don't need to include anything that the transaction didn't touch or didn't need to know about. So typically these are all very short, like one transaction only ever touches a tiny amount of the state. And then it has the marker proofs or witnesses for this data. And so like it's a complete proof that that this data or this block was fraudulent. Okay, so now let's look at a second situation. So we have the same thing again. We have this invalid transaction here, but now our full node, somehow it managed to keep this data from everyone else. So here I'm said that, like, I'll just keep the invalid transaction in block 4 secret forever, right? And so once again, we go through this a little dialogue here. So the light client would like to get this transaction 3, which is not the invalid transaction. This one is available. The node answers, and now our policeman, well, I mean, typically the policeman represents another full node that would check all this. So the other full node would have, in this case, actually noticed something's going on because they weren't able to download the data. But they can't prove that. You can't prove that you can't download data to anyone else. And so maybe they can say, warn everyone, hey, something's fishy, but now if they do that, then the light client wouldn't know, like, who can I trust? Who's the right one here? I guess in that case, they could just now check, but that's where we come to the problem, the data availability problem, the fundamental problem that's behind it. It's a non-attributable fault. So you cannot prove that data is unavailable, and it can change at any moment, either due to someone doing something or just due to network delays, like data can be unavailable even just because it hasn't arrived yet at the destination. But basically, let's look at these two situations, A and B. We have one where the one who created the block is evil, and he sent this block header but never sends this transaction. And then a nice guy warns everyone, hey, he's trying to hide this transaction. And now afterwards, that evil guy just sends the transaction to everyone and says, hey, what are you talking about? It was here the whole time. And now in situation B, we look at the same thing, except that this time, it's actually the one who created this block was the good guy, and he did include the transaction. But now the one who warns is the evil guy, and he still says, hey, it's not there. So he's lying. And once again, afterwards, the first guy says, hey, what are you talking about? It's there. Now, the problem is that the light client doesn't know if he gets a warning. He can't know which of these two is going on. Like it's impossible to know from the end result which one happened, except if you did check the whole time. So it might be if you were actually in the first situation, you were already checking. But even then, you might get it wrong because it might just be that the data arrived later. Like it might not even be something that like something evil going on at all, even if some data is missing sometimes. Right. And this makes it so difficult because you cannot, you cannot just prove that something bad was going on. And if, for example, you allow anyone to just shout out a warning to everyone, hey, stop there, some data is not available, then you basically create a huge DOS vector because now evil guys could just keep doing that all the time and clog the whole network. So yeah, so from this data available problem, the direct consequence here is that light clients lose their protection from invalid transactions because at the time the transactions and created data might be unavailable, and so like invalid data may be on the chain. But actually it's a bit more than that even. Like, so for example, some might think, oh, it's okay, like in ZK rollups, for example, we always know that the data is correct. Like it can never be falsified because there's a zero knowledge proof about its correctness. But it's still a problem actually, because the data belonging to some account, even though it's always correct, might get lost. Like there might be, nobody might know the correct witness to get that data. And then basically you can never use those funds again that are on that account. So that's still a pretty big deal if your funds get lost through such a fault. Okay, so let's come to a first naive solution, which is basically the light client says, well, what I'll do is to check whether the data is there, I'll just sample a few of the transactions and ask for a few random transactions and see if they're all there. And surely if those transactions are available, then I should be pretty safe. It should be pretty unlikely that that someone can trick me and present me with some unavailable data. But the problem is that if you only hide a very small number, say only a single unavailable transaction, that still makes the whole chain invalid, but it's very hard to catch. It's very unlikely that you will sample exactly that transaction. So for example, if you say sample 10% of the data and only a single transaction is unavailable, then the probability that you're catching this one is just 10%. And that's just way too low. And at the same time, sampling 10% of all the data on the chain is already way too much. That's what we want to avoid as a light client. They should be downloading much, much less than 10% of the data. So what we need is basically a way to amplify this method so that even with just a small number of samples, we can already be sure that most of the data would be available. And yeah, in comes erasure coding. This should be pretty familiar because most of you are very familiar with zero-knowledge proofs. The idea is basically just you take your original data and you extend it as a polynomial. So basically you take the polynomial that goes through your original data and you evaluate it at a few more points. So for example, in this case, let's take 5 data points and we extend the polynomial with 5 more points. And this is called a Reed-Solomon code, but it's nothing else than just polynomial interpolation. So the so-called coding rate is basically the proportion of the encoding, which is data. So if it's 0.5, that means 50% of the blocks would be sufficient to reconstruct the whole data, because a polynomial of degree n can always be reconstructed with n plus 1 points. And the nice thing about this is once you do this, then the sampling becomes efficient, because now the number of blocks that you need to check, the number of samples you need to take, is just a function of how sure you want to be that the data is available. So for example, let's say we take the coding rate of 50% and we query 30 random blocks. Now, if half of the data were unavailable, which is necessary in order to hide any data, because if more than 50% is available, we can always get everything. Then the probability that all those checks pass, all those studied checks pass, is now 2 to the minus 30. So that has become super unlikely. So erasure coding is the way in which we can amplify our checks so that a small number of checks gives you a very high certainty that all the data is available. And now once we come back to our picture of our light client talking to a full node. And so now they start, even before they do all this is something they basically do as part of downloading blocks. So please give me 30 random samples from the polynomial extension of each block, and then they will tell the full node here, these are all the samples I want. It is, by the way, essential that each light client will do this individually. So they will use local randomness to do this. You cannot, for example, fiat Shamir it, because then it would be easy to just take exactly those points that are queried and hide all the other ones. And those are, of course, much less than 50%. So it's essential that each client does this. So there is a certain overhead, which means, for example, in this case, you have to query those 30 random points. And then they are done with this, and afterwards they go through the normal process. And this time I drew a happy policeman here, because basically there isn't much, there could still be a fraud proof, but the nice thing is basically by this first step, the light client has already made sure that this data availability problem cannot occur. They know that more than 50% is available of each block. So they are like, well, it's good that I've done all these checks, because if there had been an invalid transaction, I now know that the data would have been available to everyone. And so there would have been some full node that would have alerted everyone and created this very simple fraud proof that shows to everyone that that some invalid data was on the chain.
So can I ask a question? So there is an assumption
Sure.
here, right? And that is that, so if the block is invalid and the data is not available, then I can still, as a set of validators that are doing that shard or whatever, that chain, I can still fool some light clients by giving them the random things they ask for. Right?
Okay, so this is okay. So now there's a distinction that is true, right? So if we assume that you control which requests are fulfilled, so let's assume that this full node both created the chain and is satisfying the light client requests. Yeah. So in this case, you are right. In this case, I could fool a finite number of light clients. Like, so unless I give more than 50% of the data away, I can prevent them from getting everything. So that's true. Yeah.
And this is an issue if our light clients are basically going to be other chains and other high value targets.
Right. Yeah. So yeah. So basically, so this depends, right? So this will, if there are, if like you can prevent this by basically, so one of the possibilities is that you say there is like a peer-to-peer network out there into which you have to upload all this data, and that is the one that is satisfying these requests. So it's kind of a neutral storage that you have. Yeah, but you're right. So that is a limitation, but it's also, you can only fool a small number of light clients, basically. Yeah. Does that answer your question?
Yes.
Right. Okay. So now I'll come to why this is so important in the sharding design. So far we have like talked about light clients, and people might be, yeah, like, how does this concern me if I run a full node? But basically, so in Ethereum 2.0, just here's a very rough overview of how it works. We have this beacon chain, which is basically there to coordinate things. So for example, validator registration, and basically sending validators onto shard chains and tell them to go in a committee and check what's going on there. And then we have all those 1024 shard chains, initially 64, where the actual action happens, like this, where actual transactions would be. So all validators check the beacon chain, and yeah, validators are assigned in committees to check the correctness of shards. So if I'm a validator here, then I validate the beacon chain and one shard, which actually means for all the other shards, I'm a light client. So although we would call validators full nodes in Ethereum 2.0, they are actually light clients on most of the shards. And this is in many ways essential for scaling blockchains, because the fundamental bottleneck of blockchains in the end is that in the current designs, everyone checks everything. And that fundamentally limits like the throughput of the blockchains to whatever spec validator you allow to validate everything. So typically this is, we want that you can do this at home on your laptop, and that's just the fundamental limitation on how far you can scale. So basically this is essential if you want to keep that. And so that has the same implications as it has for the light clients we talked about previously. You need to rely on fraud proofs to know that everything's correct, that is that there's nothing bad going on the other shards. And we also need to make sure that the data is available so that the fraud proofs can be produced in case there's fraud. So basically, you shouldn't be confused by this terminology between light clients and full nodes. So it's good to, basically it's much easier to explain all the data availability terms in the light client full node sort of schema, but it actually applies in almost all blockchain scaling systems, that if you want to scale your blockchain, you will have in some way this problem, because you don't want that every node has to be able to download everything. Okay, so there's one little part that we skipped here, So this erasure code solution is very elegant, but the problem is, how do we know that whoever created the erasure code did that correctly in the first place? So how do we handle the case where the block producer, for example, or whoever produces the erasure codes in our system, will actually extend it as a polynomial instead of just making up some data and claiming that the whole thing is a low degree polynomial, essentially. So in our picture, what would happen is light client asks for some samples, and then the evil full node gives them some random garbage, essentially. Now our policeman says, oh yeah, you have random garbage. So now the only way to actually show that in the, if the whole thing is just as what a polynomial is, to just give, well, at least 50% of the data, which is a huge amount of data as the assumption. So that's not very practical. So basically our light client is stuck, like, who's right this time? In theory, he could check, but that would be expensive. I'd have to download all of this data. So yeah, this is kind of where I'd say the action is now in terms of data availability proofs, because like the basic idea of having erasure codes is kind of quite obvious. But now how do you solve this problem of proving that the encoding is correct? I guess the almost obvious solution would be like just snark everything. This is not so easy, because we're talking about pretty big amounts of data, and we need to hash all of that, and so that's a pretty big zero knowledge proof. So this solution isn't quite practical yet, at least for the amount of data that we need in Ethereum 2.0. For smaller schemes, it might well work. The solution 2 would be to that's somewhat more feasible, that we just use the commitment schemes, polynomial commitment schemes themselves, to commit to the data as well. And then the part that it is on a polynomial is kind of a given just by the commitment scheme. Problem is that then generating witnesses for data becomes somewhat more expensive, because proving something in Kate, for example, is a lot more expensive than giving a Merkle proof. And solution 3 is to use a different encoding than one-dimensional Reed-Solomon codes, so that the fraud proof somehow becomes shorter. There's one very interesting solution that is the coded Merkle trees paper, and the other one is the two-dimensional solution, which I'll come to in a bit, and that is the one that we're currently still favoring at Ethereum, which is you basically, instead of using a 1D polynomial, use a 2D polynomial. So you have basically the data in one corner here, and you extend it in 2 directions. And the nice thing is to prove that something is not a 2D polynomial, giving either one row or one column of data blocks is always sufficient. So now you get relatively short fraud proofs, so it's easy to prove if someone gave an incorrect encoding. The problem with it is that the stopping rate becomes a lot worse. So if you want that 50% is always enough to reconstruct all the data, then you actually need to extend it by a factor of 4 instead of 2. So you basically get a lot more data on the network. But yeah, it's currently still the best compromise. All right, that is my presentation. Please feel free to ask any questions.
Yeah, so doesn't your work with Dmitry solve the, I mean, make the getting the witnesses in Kate pretty good?
So it does become a lot more efficient, that's true. And it is actually something we are still exploring at the moment. So it's yeah. I mean, it's still a lot more. Like it still costs a lot more than for example the 2D scheme to compute. Like basically it comes down to the question of whether you're happy to tolerate that you need some, I guess, more powerful nodes that do some computations for you. So for example, the Cara scheme would probably be okay if you said, well, I guess it's okay if we only have some super nodes which compute this. It's fine because there's basically no way for them to cheat and we can check all of their computations pretty easily. So yeah, so that's basically the trade-off, but it would mean that normal validators would have no chance to compute the data availability roots. Yeah.
I mean, but is this 2D, right? This 2D thing, you need to compute some like bivariate extension of the data.
Right.
And your thing of all the proofs for Kate, it's like linear. Yeah, it's linear time, but group operations instead of field. But you're saying
It's,
like to
it's
compute this
n log
2D
n.
extent.
No,
Okay.
It's still n log n group operation. It's actually, so it's a little bit worse, unfortunately, because yes. So I mean, asymptotically, it's n log n. But actually the constant is a bit worse because you actually need a matrix multiplication with dimension 2n.
So do you have like an estimate, like in terms of constant, like how much more expensive is it to do that than to do this 2D extension?
No, I don't have concrete numbers on those. No, sorry.
But you estimate it's like 100 times or something, or maybe,
that is a very good question. Right. So yeah, I mean, it would be similar to the difference between field multiplications and group operations.
Yeah.
But it's actually a bit worse because we can do the 2D scheme in binary fields, which I think are quite a bit more efficient.
Yeah.
But that doesn't mean, like, I mean, we are currently exploring actually, like, we are exploring polynomial commitment schemes for many things. So, I mean, I wouldn't count them out yet. I think, like, basically what may kind of tip the balance here is that, for example, if we are already using it to, so for example, one of the problems is we want to go to this completely stateless approach where we basically give witnesses for everything. And now it's turned out that using Merkle proofs, that will actually lead to pretty big witnesses. Whereas like with polynomial commitment schemes, it's more Kate, it's basically always just one group element. So that's super nice. So that may yet tip the scale in the favor of polynomial commitment schemes. And once you already use them to commit to your data, then it becomes obvious that you'll also do this for the data availability. So it's still well possible that this will happen. Yeah.
So one of the assumptions here is, so as light clients, the validators of other chains are going to be sometimes interested in small pieces of data. I presume that's why you need this check at all. Because if people were only interested in having the whole data, then people could check the erasure coding from any commitment, like a Merkle tree of the erasure coded pieces.
Right. But I mean, why would a validator need the whole data of a shard chain that they're not currently validating?
They wouldn't, but why would they need a small piece of it?
They don't either. They just need to know that it's correct. So basically, you can get slashed as a validator, for example, if you attest to a beacon chain block that includes a crosslink to a shard block that's incorrect. And this is necessary because otherwise we couldn't give all those guarantees.
And you necessarily have to be able to prove this by 4 proofs, which have to be sure. Okay, yeah. So in Polkadot, we don't do this. We do erasure coding, but we don't need this.
Yeah.
Because we're not attempting to do small 4 proofs.
Right.
Dankrad, there is a question in the chat.
Mm-hmm.
Let you read it.
I haven't read the chat yet. No. Let's see. Where do I?
I can read it if you want.
Yes, please do. I can't currently see it.
No problem. Why can't we use validity proofs for proving transaction like in some L2 solution? Is it because the amount of data is way too large?
Is that validity proofs as in zero knowledge proofs or what?
I'm assuming that refers to computation integrity proof in general, which
right. Okay. I mean, so it depends, but I think like for Ethereum in general, the answer is that currently it's not feasible or it's very, very expensive at least, to have general execution inside, computational integrity proofs. That is, I mean, yeah, I think that's still, I haven't really seen any viable zero knowledge virtual machine yet. And I think I suspect it will be quite a few years until that exists. If it only refers to validity proofs as in proving that the data is correct, that is essentially what we're already doing by making all the shards stateless. So all state that is accessed in a shard will always come with a full witness that shows that the data is correct.
So I believe I mean, from my understanding, you answered the question with the VM. I think indeed it's not, I mean, as far as I know, there is no general computation available, a VM on that would be able to power a general purpose blockchain. I have an extra question, which is something that I have very hard time getting around, and I would love to, because the likelihood discussion is very important in this context, is what is a consensus rule apply in the shard, in shard? Like, how do I know, how can I be a light client? Because I'm assuming it's not the longest chain. What is the consensus? How does it work?
Right. So actually, the consensus, so as a light client, you would actually always follow the beacon chain, which will refer you to a shard. So you would never actually really be following one shard on its own.
The related question I have, which I think you pretty much need to do to answer this question is so what happens on the consensus layer if it turns out that a shard block is unavailable, if the validators don't get their pieces?
That means that, this is part of the fork choice rule, right? So, okay, so this is maybe one essential thing that I haven't really touched on. The only way to implement data availability checks is if you make them part of your fork choice rule. So you basically need to say that any block that does not pass data availability checks is just not part of your fork choice. So they can never be on the chain that you currently consider the valid chain.
So obviously the next question is can this be just one cross link out of the 64 I have in a block?
Yeah,
Does it make the entire block disfavored?
Yes. So I mean, this touches on another thing. I mean, there's obviously still the question that is not 100% answered. We have a tendency there, but whether you want to construct data availability for per shard, like on every shard, or are you going to do it once they're cross-linked all together? The second one is obviously more efficient because you need to do only 30 checks instead of 64 times 30 checks. So that's a pretty big difference. But then of course it comes with the question, who does this and so on. But yeah, anyway. But yes, if you did go for the solution where you do it per shard, then any shard block being unavailable would mean that the beacon block is just invalid. It's not considered a valid block at that point, which can change. So data availability is actually something that can change, right? So if more blocks become available, then it might actually be considered valid. And this is necessary because basically one of the conditions that we have on this, that in the end, everyone should converge to the same view. And that means obviously someone can create the condition where some clients see something as available and some don't see it, because this is probabilistic, right? But what we know is in this condition that if some clients see it as available, there's a very, very high probability that it is available and they can reconstruct it. So in that case, they should download enough data in order to be able to reconstruct it and then reseed it so that everyone will see it as available, so that everyone converges to the same view.
Yeah, so we had this problem on Polkadot, that basically that one shard could, if the validators on that cooperated, they can release something unavailable and make they can kind of choose whether something happens by withholding the erasure coded pieces for one thing until later. And then they can come across, they can put it later, and then this thing happens. And if they don't want the thing to happen, because then they can withhold them. And this leads to problems with trying to get an invalid block in, but trying to make it not happen if anyone detects it. If anyone tries, if the wrong people try and reconstruct it, then you can detect that they try to reconstruct it, and then you just made the whole thing not available.
Right.
And this caused a lot of problems for us.
Okay, let me. Can you repeat that? So the block is, so they create a block. Someone evil creates a block.
Right. So we create one block. We withhold the pieces. And now at any point later, we can hand out the pieces, and that makes this particular beacon chain block valid now.
But you said it has invalid data.
No. So what you can do is you can have a different block in a thing in the same, with the crosslink in the same block, but has invalid data on it, or something like that. And now you can make it, you can make the entire block unhappen by not.
I don't understand how the block, because I mean, surely you committed to the block. So
yes, you committed to the block. Okay, so here's one attack, which is we have an invalid block.
Yeah.
And we have the correct erasure coding of our invalid block.
Yeah.
And now we wait to see who's going to ask for all the pieces.
Yeah.
They're probably going to ask everyone for all the pieces. And we don't hand out any pieces until we think that no one's going to check it. And then we can get an invalid block in only when no one's going to check it. And when someone does check it, then we withhold the data. Now, that means that the fork truth rule is going to disfavor this block. But on the other hand, we're not going to get slashed, because we don't get slashed for being responsible for the availability of something that we can't verify the availability of, because basically we can't prove.
Right, but how is this block a problem? This is just a block that doesn't exist essentially now.
Right. So what we want is a situation where if the block is invalid, it doesn't exist. If someone's checking the block, it doesn't exist. But if no one's checking the block, it does exist. And these effects
but the point, okay, right. So this is the point of data availability checks. They only work if everyone makes this part of their fork choice rule. everyone, like full nodes and like clients, they always do these checks.
Yeah, so the issue for us was that, so basically using this, you can make sure that you don't actually commit to something until you know who's going to, who you think might be trying to check. And there where you only get slashed when when your block is successful in the short run. So the idea was to do an attack with a small fraction of the stake in the system.
Right.
That end up being profitable only if you don't get, if you only get caught when your attack happens. And that was annoying. It might not be the same with Ethereum. You might have a different attack model than we do.
Yeah, I'm still confused how it could happen because, like, as I said, in our model, everyone would do those checks all the time. So all the nodes always do the checks. So
for data availability, yes, but not for validity of blocks on shards.
Right. I see. Okay.
So the model is that maybe we have some colluding parties. Yeah.
Okay, you're saying
who are trying
that you satisfy everyone who makes a few requests, but you don't satisfy those who make a lot of requests.
No. So basically, you satisfy everyone.
Yeah.
If you determine that no one is trying to get all the pieces.
Mm-hmm. Right.
But
then the probability would already be very high that everyone together has gotten enough data to like just reconstruct it, and it nevertheless.
Yes, they have enough data, but no one's checking it in the short run.
Right. I see. Right.
That was the issue.
Okay. So the point is, of course, that on every shard we want to have enough validators that. So I mean, so all of this, what we're talking here about, is already a kind of a consensus failure, right? So like, we don't need fraud proofs if we trust that 2/3 will always be fully honest and check everything, because then like something not being available can never exist. So we are already in a situation essentially where we say like 2/3 might on a shard or so, like 2/3 of a committee on a shard are trying to be evil. That's already a precondition here. Now the question is like, the assumption is that even if that happens, at least someone will be on a shard. Even just a single node is enough to create that fraud proof, and they have a duty to do it. Like everyone on the shard should be downloading the full data.
Absolutely. Just the downside here is that we're going to know when they exist and when they don't exist.
Right. Yeah. Yes.
Because they're going to be trying to reconstruct. They're going to be trying to get 50% of the pieces, and they're going to have to, basically, they're going to ask everyone for this. So they're going to ask the bad guys too.
Yeah. Yes. Right. Yeah. Yeah. So, but basically, I mean, that is what we're doing. We are reducing the fraud proof plus data availability picture reduces a like 50% honesty assumption or whatever it is, with one honesty assumption, that there's at least one honest full node in the world.
Agree, but this attack was more about trying to.
So I mean, it sounds like you're trying to detect whether that one honest full node exists.
Yes, in order to like, so the actual model we were thinking of is more or less, can we get our economic security up to that of the entire chain?
Right.
But the problem is that only 1/64 of our validators of our stake is backing this chain. We can make the expected cost of attack expensive if we make the good guy, the attackers basically commit to this thing they're doing, and then only afterwards work out whether they're going to be detected, and make it so that, you know, in at least in more than one, well, you know, is that we catch them a lot of the time, but the attack only succeeds less than 1/64 of the time.
Right.
Then the expected cost is...
The one thing that makes me very little worried about this, because I assume there will be a few entities in the world which just check everything all the time. right? Like
Yeah, and that
we
gets
always have a blockchain explorer that just wants to download all the blocks no matter what. So your attacker is already in a pretty bad situation here. If they try to stop that, like I think they're already screwed.
Yeah, it's a little bit because of yes, absolutely. The question is, how fast do they do it? How fast do they generate fraud proofs?
Right. Yes. Yeah.
So this is a limit. So if we finalize an attack block and then it gets acted on, then they might make some profit out of this attack, and it's that we wanted to make expected. Anyway,
yes,
in Polkadot we have the solution.
Finalizing a fraudulent block would be pretty bad. Yes. So that.
Yeah. So in Polkadot we literally had to have people randomly checking after we decided something's available.
Mm-hmm.
And then leave some time for them to check before we actually finalize something. Mm-hmm. This was the model we
randomly
came up
checking with. As in checking the validity.
Yeah, checking the validity of a random other block. A random block on another shard, let's say.
I see. Okay, interesting. So wait, so you have 2 levels of committees? Is that?
Well, no. So more or less, but it's more that there's 2 levels of deciding. We decide on availability first,
mm-hmm.
and then check.
Okay.
So that the people have committed to availability, and they can't do this withhold until we discover who's checking attack.
Right. I mean, would be interested to talk about this in more detail. We have like.
But yes, it's kind of a detour at this point. Yeah.
Yeah. Thanks very much. I'd be interested in talking through that. Yes.
I will leave you, Alistair, and you guys take it offline. Is there any more question?
Yeah.
Actually, there is a question which I'm about to ask you offline also, but would be the slide available? So we have a support to make them available. So could you share them with me?
Sure, I can do that. Yeah.
Awesome. So the slide for everyone to listen now, the slide will be available either on the Facebook group as usual, as well as the recording, which would be on YouTube. So the slide will be on the Facebook group and on the Telegram chat that I posted, a chat/announcement group that I posted on the chat on Zoom. And the video would be on YouTube on the link that I shared before, which is Zero Knowledge Group. There is an additional question from Garance, which is, what do you mean by stateless sharding? And I think probably is going to be the last question.
Mm-hmm. Right. So basically, we have more or less made the decision that the shards are going to be stateless from the perspective of validators. So validators are the nodes which form the consensus. So they are on committees and check that a shard prologue was valid, and then cross-link it to the beacon chain, which basically means it's final and is on available to other shards as well. And we want that they don't have to keep any state for the shards. And there are strong reasons for that, because if we can do that, then that means we can very quickly reassign them from one shard to another. So like they can just hop from one shard to the next, and because they don't have any state, that doesn't matter. It doesn't matter which shard they are on. So it has many very strong advantages. And so basically that's what we're going to do. Like there's not going to be any permanent state on the shard, or almost none. They sort of, whatever the actual execution engine does, it has to prove all the, it has to include all the witnesses for the state that it wants to keep.
So is it similar to some extent to stateless Ethereum? Are you moving part of stateless?
Yes, that's so stateless Ethereum is the same effort for ETH 1.0, which would also is a prerequisite for our next plan, which is to have it as one shard on ETH2.
Yeah, so basically, the tech that is developing today on stateless Ethereum would be reused for every shard on the Ethereum.
Not quite. So we don't really want to use the EVM on all shards. So that will be in a way a legacy shard on which the current ETH 1.x, as we call it, would run statelessly. And then the other shards would come with a new execution engine.
Awesome.
Based on WASM.
Has anyone had a question? I think we're done. So thank you very much, everyone, for joining. Thank you, Dankrad, a lot for your time. It was very cool and useful. Everything will be available on Telegram, on YouTube, etc. I just want to thank you, everyone, because we were like 44 today at 46 at the peak, and it was very terrific talk. So thanks you very much.
Thank you, everyone.